So we are going to continue talking about transient analysis of first order circuits. And we technically have 3 class periods dedicated to this material. And I feel very strongly that we will actually finish all of the lecture material today. So that means next Monday, we will just have an in-class assignment and then a lab, no real me talking at you guys unless you particularly want it or need it, which you shouldn't, okay? All right, so the first thing that we are going to talk about today is the concept of a time constant. So we learned that for a generic RL circuit, like so, let's define this to be IL, VL, VR, and IR. So we learned for a circuit like this, generally speaking, all of our response signals, so the voltage drop across the resistor, the current flowing through the resistor, the voltage drop across the inductor, or the current flowing through the inductor, would be of the form y at 0 minus for t less than 0 minus, and y at 0 plus e to the negative r over L t for t greater than or equal to 0 plus. And we spent a considerable amount of time deriving that Wednesday, because today is totally Friday. And then we also, at the end of class, looked at an RC circuit where we had some voltage source connected to a switch, which opens at t is equal to 0. And then some resistor and capacitor like so. So here we would have VC, here's VR, here's IR, here is IC. And in this case, we found that our response voltage or current through the resistor or the capacitor would look like y at 0 minus for t less than 0 minus, and y of 0 plus e to the negative t over RC for t greater than or equal 0 plus. So effectively, both of these equations are identical, except for one very small thing. The rate at which the exponential decay occurs depends on our component values. Everything else is literally exactly the same, okay? So because these things behave so similarly, electrical engineers have developed a quantity called a time constant that simply relates that rate of decay. And it really doesn't matter, like from an engineering perspective, we don't care if it's an RC circuit. We don't care if it's an RL circuit. We just want to know what the rate of decay is so that we can quantify it. Okay. So the time constant tau is the amount of time it takes for our signal to decay to 36.79% of its original value. Now, you are probably wisely asking yourself, well, where the hell did 36.79% come from? 36.79% is e to the -1. That's it, okay? So effectively, if we have some signal let's call this guy right here y of t over y of 0 plus this ratio. In 1 tau, the ratio falls to 36.79%, and this is governed by e to the -1. In 2 time constants, we have e to the -2, which is 13.533%. In 3 time constants, our signal will decay to a value of e to the -3, or 4.98%. In 4 time constants, we're down to 1.83%. And in 5 time constants, we're down to 0.67%. This is where we're going to stop. Why we're stopping here is because it's generally accepted within the electrical engineering community that 5 time constants represents t is equal to infinity. Our signal has decayed to less than 1% of its original value, which implies that our capacitor has transferred over 99% of the energy that's stored, or our inductor also has transferred over 99% of all the energy that it has stored. So that's why when we were talking about things yesterday, and I said a long time after the switch has closed, we actually have a numerical value for infinity in these cases. Depending on what our time constant is, this can be somewhere in the range of a couple of seconds to a couple of minutes to a couple of nanoseconds or something like that, just depending on what our resistor, inductor, and capacitor values actually are. Okay. So for an RL circuit, our time constant tau is simply L over R. So it is the inverse of the thing that's being multiplied by T here, right? Because we want it to be in one time constant, we have e to the minus 1, okay? For an RC circuit, our time constant tau is given by simply R times C. And just to reiterate, because I asked this question on your exam pretty much every year, 5 time constants is how long it takes for a signal to decay to less than 1% of its initial value. Okay. All right. So what this means is that we can consolidate our equation and now have a single equation that works for both RL and RC circuits. And that is simply y of t is equal to y of 0 minus for t less than 0 minus, and y of 0 plus e to the negative t over tau for t greater than or equal to 0 plus. This relationship is what's called the natural response of a first order circuit system. So what we are going to start talking about now is what's called the total response of a system, okay? So in all the examples that we have worked to this point, our circuits have operated in such a way that the switch effectively removed the excitation source from the system. So we're going to talk about what happens the opposite way around. What happens if the switch adds in an excitation source, right? So let's consider this circuit. Let's say that this is VC, this is IC, and this is IR, okay? So this is exactly the opposite of what we had on Wednesday's class. Instead of the switch opening up and disconnecting our voltage source VS from our capacitor, now our switch is closing, which will connect the voltage source VS to the capacitor. So if we're looking strictly at our capacitor voltage equation, what do you guys think VC at 0 minus is supposed to be here? 0 volts, because there was nothing connected to it. So that seems pretty reasonable. What about VC at 0 plus? So you said 0 or VS. Which of the two is it? 0. Why is it 0? Exactly correct. The voltage drop across a capacitor cannot change abruptly, much like the current through an inductor cannot change abruptly. So whatever value VC had at 0 minus, it must also have at t is equal to 0 plus. Now here's where things get interesting. Okay. What value is the capacitor voltage going to have is equal to infinity a long time after the switch has closed? Yes, because they'll be connected in parallel and our transient will have died out. Okay. So what we have effectively discovered here, if we were to plot things, would be something like this. Okay. So here is VC as a function of time. Here is time. Here is 0. And let's consider here to be infinity. So our value is 0 all the way up until we hit t is equal to 0. We know that we're going to have a value of Vs once t reaches infinity, or really 5 time constants. What do you think is going to happen in between? So in class on Wednesday, we mathematically derived that a capacitor discharges following an exponential response. Does anybody see any reason why a capacitor shouldn't charge following that same exponential response? No. So what we're going to have is something that looks like this. Okay. This quantity VC at infinity is what's called the forced response of the system. The reason it's called the forced response of the system is because a forcing function, in this case our DC voltage source, is forcing our capacitor voltage to have a non-zero value at t is equal to infinity. So we're settling to some value that is not 0 because our capacitor, once it reaches DC steady state, still has some amount of energy stored in it. We would see the exact same thing if we were looking at an inductor circuit. Okay. Our total response is simply the natural response plus our forced response. So it's a combination of what the circuit would behave like if we didn't force it to do something, plus the effects of forcing it to do things. Okay. Mathematically, we could describe this for this particular capacitor as VC as a function of time is equal to, and so I'm going to ask you guys to not write things down just yet because I'm intentionally making a mistake here. Okay. So if we follow this definition here exactly, what we would wind up having would be y at 0 minus for t less than 0 minus, and then y, or excuse me, VC at 0. Let's use VC. My apologies. At 0 plus e to the negative t over tau plus VC at infinity for t greater than or equal to 0 plus. Now there's a mistake here and it's not super obvious, okay? The mistake here is that our capacitor voltage is not a continuous function anymore. So at t is equal to 0 minus, we have some value, right? We know that it's supposed to be 0. If we evaluate this bottommost expression at t is equal to 0 plus, what we will find is that we have 0 times e to the negative t over tau, which looks like 0, plus some DC value. So effectively, our capacitor voltage instantaneously is jumping from 0 up to its DC value. So we are going to correct this. We scoot this stuff over a little bit by changing the coefficient that's multiplied by our exponential function. So this is going to look like VC at 0 plus minus VC at infinity. We're performing this mathematical operation to force this to be a continuous function in time. Okay. From this, generically, we can say that y of t is then y at 0 minus for t less than 0 minus. And then we'll have y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. This is our generic equation. We don't have to change the steps from our analysis that we developed on Wednesday at all. If we analyze the circuit at t is equal to 0 minus, we analyze the circuit at t is equal to 0 plus, we analyze the circuit at t is equal to infinity, and then we calculate the time constant, finding REQ, LEQ, or CEQ. All of those pieces of information just get plugged into this equation directly, and we are done. This is all of our first order circuit material. So from here on, it's just example problems. And because my Surface is about to run out of batteries, I'm gonna let you guys start working on your in-class assignment while I pop across the street and go get my charger. And then if we need to work example problems with me showing you what to do, I'm happy to do it. But my computer is definitely going to die soon.